So 3/5, 3/10, derivatives handout.
Do we have to turn that in?
I'll collect it,
Okay.
but I don't ask for it right now in case people have questions. Probably helps to look at it, you know what I mean? Lucas.
Number 3 in the derivative packet.
Sure.
I don't know if there's going to be one.
Tomorrow?
All right. So it says f and g are twice differentiable functions. What does that mean? Just that we can take the derivatives of them 2 times if necessary. It says g of x equals e to the fx. G double prime of x is h of x times e to the fx, and we want to know what h of x is. So let's just start by taking the derivative of g. We'll do that 2 times and see what we get. So if I take the derivative of e to the f of x, I recognize to do the derivative of that, I need to use a chain rule because I see one function composed inside of another function. F of x is inside of the function e to the x, right? To do the chain rule, I do the derivative of the outside function. The derivative of e to the x is just e to the x. So I have e to the fx, and then I have times the derivative of the inside function. The derivative of f of x is f prime of x. Everybody feel good so far? Okay. So now I'll take the second derivative. To take the derivative of e to the fx times f prime of x, I need to use a product rule. So I have the first function times the derivative of the second function plus the second function times the derivative of the first function. So far, so good. What's the derivative of f prime of x? F double prime of x. And the derivative of e to the fx, we already did, it's right there. So I'll just drop that in there. So far, so good. So that's my second derivative of g. If I look, I notice that I have an e to the fx in common with each term. So if I factor that out, I'm going to have a f double prime of x plus, I have an f prime times an f prime, that's f prime squared. So what I'm left with, that must be my h. Oops, if I picked the right one. So it should be D. Does that make sense, Lucas? Everybody else okay? Cool. Others on questions? John Paul?
Can you do 12?
Same thing on the sheet?
On the sheet.
Okay. Sure. No, come on now. I did not do that. I copied that. You guys all saw me. All right. So it says that if f of x equals a times e to the negative ax, then f prime of x equals what? Okay, well, let's start by taking the derivative. Here we're told a is just a constant. So if I'm taking the derivative of a e to the negative ax, I can just pull the a out front. When I look at e to the negative ax, that is a composition of two functions, e to the x and negative a to the x, or ax. So I know that I have to use a chain rule there. So the derivative of the outside, the outer function is e to the x, so that doesn't change. And then I have times the derivative of the inner function. So the derivative of negative ax is negative a. So when I combine my like terms, I have negative a times a, which is a negative a squared, and then I still have that e to the negative ax. So it looks like we'd be going with option E there. Does that feel okay? Violet, is this a follow-up to this one?
No.
Different question? Okay. Well, you're next, Alex, then. 5. I think I have 5 already on the other page. Yeah, okay. Okay. It says that f of x is equal to x squared plus 2x. Then the derivative of f of the natural log of x equals what? Well, let's just start here. So when I look at that, it's an obvious chain rule, right? Because I have f is the outer function and ln of x is the inner. So far, so good? So the derivative of the outer is just f prime. And the derivative of the inner, the derivative of natural log is 1 over x. So far, so good. Now, I'm just going to calculate f prime on the side, which is just 2x plus 2. So when I do this, I'm just going to be plugging the natural log into the 2x plus 2. And if I simplify that, they didn't do any nasty logarithm rules there, just looks like that option A. Does that make sense as to what to do there? That's probably the simplest way to do it rather than starting with the composition and then doing the derivative. That gets a little messy. But you could do it that way. It's not wrong. Alex? 13. Ooh, I think I probably have that one too. Okay. It says if f prime is equal to yada, 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 and g of x is equal to this, what is g prime of 2? Well, let's start with, come on now. Start with calculating g prime. So this is clearly a composition, right? So we have to use the chain rule. So the derivative of the outside is just f prime. And then times the derivative of the inside. So the derivative of x squared minus 1 is just 2x. So now I'm going to plug in 2. 2 squared minus 1 is 3. And 2 times 2 is 4. And now to do this piece, I'm just going to be plugging 3 into that. So far, so good. So those guys simplify out. 3 squared is 9 and minus 4 is 5. 3 minus 2 is 1 and 1 cubed is just 1. So I get just 5/4. That feel okay there? So again, like tempting to like put stuff together too soon if you just are a little bit patient about that and go in a, like knock the symbolic calculus parts out and then plug things in. Life is usually a little bit easier. The last thing I'd want to do is try like plugging the x squared minus 1 into that thing. Yuckarooskies. Selena? Sure. John Paul, is that a follow-up or a new question? Okay, you're next. All right, you guys spent some time on this sheet then, huh? That's good. Sure. All right. And what did you not like about this one?
I don't know, I think you need to do story.
Okay. So the thing that sticks out to me right away that I'm a little bit concerned with are the absolute values. What do you think the absolute value is really there for, though? To make sure it's positive. Why would that be important? Because I can't take the natural log of a non-positive, right? So 0 is also a problem, but negatives are a problem. Can't do the log, any log of a non-positive number. So that's really what that's there for, is to just make sure you're not doing the derivative of something undefined. Make sure that it's a defined function. So I can largely just kind of ignore that absolute value, I think. So if I look at this, it really looks like the composition of 3 functions, right? My outermost is the natural log, and then I have a cosine, and then inside of that cosine I have a pi over x. You guys see that? So that's going to be the derivative of the outside. So the derivative of natural log is that times the derivative of the inside. Now, the derivative of cosine is negative sine times the derivative of the inside. And I'm going to write pi over x as pi times x to the negative 1. Is that okay there, Selena? Just to make it easier to do the power rule. So that guy comes down. This guy comes down. We have negative 1 pi x to the negative 2. So what do we have here? We have negative sine of pi x over cosine pi x times negative pi over x squared. Is that okay? Do you recognize sine over cosine? That is tangent. That's a trig identity that we'd expect to remember. And then I noticed that the negatives can cancel each other out. So this looks like that boy right there. Does that feel okay there? Sure. Paulo?
14.
Oh, I'm sorry. John Paul was next, though. We'll get to you, though. What one? 25? Okay. Ah, one problem short. Okay. It says the function f is defined by f of x equals x over x plus 2. What points on the graph of f have the property that the line tangent to f at xy has slope 1/2? So when I see slope 1/2, I'm thinking we're going to be solving the derivative equal to 1/2. If I want to find the x's where the slope is 1/2, everybody good with that plan? To do the derivative, I need to do the quotient property. Yeah. So we have the bottom times the derivative of the top minus the top times derivative of the bottom all over bottom squared. So when I do that, I just get 2 over x plus 2 squared. So if I just kind of like cross multiply, I get x plus 2 squared is equal to 4. If we square root both sides, I get x plus 2 is plus or equal to plus or minus 2. So x would be 2 minus 2 or 0, or x would be negative 2 minus negative or minus 2 or negative 4. So those are my x values, 0, comma something, and then negative 4, comma something. How do I find the y's? Plug it back into the original. So if I plug 0 in, I get 0. If I plug negative 4 in, I get negative 4 over negative 2, which is just 2. So it looks like that one. That feel good? Okay. Paul, you wanted 15?
No, you already answered 15, so I think that's...
Oh, okay. Others with questions on stuff. Homework, packets, other things, favorite color. Lucas. 28. Yeah, sure. Okay. So this is like an implicit differentiation problem. Ooh, 28 and 29 are the same problem. That's weird. So we'll take the derivative with respect to x of both sides. The derivative of 3x with respect to x is 3. The derivative of tangent y with respect to x is secant squared y times dy dx. right? Is that right? Derivative of tangent secant squared. Okay. Now we just have to get the dy dx by itself. So I'll subtract 3 from both sides. And then I'll multiply by negative cosine squared. Why negative cosine squared? Because secant squared is 1 over cosine squared, right? Multiplying by cosine squared would be the same as dividing by secant squared. You guys okay with that? Those trig identities matter, huh? They absolutely do. So there, we're at the end. That feel okay, Lucas?
Yeah.
So again, if you add 3 over secant squared y, that's still the right answer, just not the multiple choice answer they're looking for, right? It's correct, it's not simplified as far down as they did. Others with questions? John Paul?
The last one.
The last one. Okay. All right. It says if yada, yada, yada equals yada, 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 then at x equals 1/2 and y equals 2, what is dy dx equal to? All right. So we'll just start by taking the derivative with respect to x of both sides. So far, so good. If I look at the derivative of e to the xy, what do I see there? A chain rule, right? The outer function is e to the x and the inner function is x times y. So derivative of the outside times derivative of the inside. What's the derivative of y squared? 2y dy dx. What's the derivative of e? Nope. Nope. 0. Why is it 0? It's a constant. Oh. And obviously derivative of 4 is also 0. Tricked you there. All right, we still have to do the derivative of xy. How do I do the derivative of xy? That's a product property, product rule. So we have like x times the derivative of y plus y times the derivative of x. What's the derivative of y? It's 1 dy dx. What's the derivative of x? 1. Okay. I'm going to distribute that e to the xy through now. Actually, I'm not even going to bother doing that. Oh, stop it. All right. So I'm done with the calculus. I'm now just going to plug those in. So x is 1/2 and y is 2. Looking good so far. I'll distribute that e through. I'll subtract the 2e over and also factor the dy dx off the remaining pieces. And then just divide both sides by e over 2 minus 4. Now, unfortunately, that's not what any of my answers look like, right? So what I'm going to do is, I notice there's no like fractions inside of fractions there. So I'm going to start just by clearing that out of there. The easiest way to do that is multiplying the top and bottom just by the greatest or least common multiple of all the denominators. So the only denominators are 2 and 1. So the least common multiple is just 2. So that gives me negative 4e over e minus 8. Now let's go look up there. Do I have that? Nope. But I noticed that, yeah, I could multiply by negative 1 or factor a negative out or whatever you want to think about it. That's the one I want. Just like in Greece, right? Some musical theater jokes for you. No? Okay. One smiling person. What's up? Oh, yes. So again, lots of places where I had a correct answer. It's just about keeping going until I get one of the answers that they have. You know what I mean? Be careful about these implicit differentiation ones. They are some sneaky little buggers there, where we try to hide in those product rules and chain rules, and got to remember your dy dx's, and lots of places to get you to make a mistake there by being very sneaky. Okay. Last call on questions. Anyone else? All righty, very good then. Let's do 3-6 then today. This will be a quickie, considering we've already kind of done it. Because I showed you the differentiation rule for the natural log already. That's kind of the takeaway here from this. We're going to start with the more general version, though. So the first derivative rule we're going to look at here is the derivative of log base a of x is equal to 1 over x ln a. Notice if this is the natural log, a would just be e. And what's the natural log of e? 1. So it just turns into 1 over x, just like we knew before, right? All right, let's look at how to do this. So I'm going to start first by using my definition of a logarithm. So if I say, well, if y is equal to log base a of x, I can say then that a to the y is equal to x. Everybody's okay there? That's just our definition of a logarithm, back from like algebra 2. If I then take the derivative of both sides, if I do the derivative of a to the y with respect to x, That's going to be a to the y times the natural log of a times dy dx. And then the net derivative of x is just 1. So if I divide both sides now by a to the y times the natural log of a, I have this. And what is a to the y the same as? X. So that's our proof. Just taking advantage of that property of logarithms and the chain rule, or implicit differentiation, however you want to describe it. So it's the same, 6 of one, half dozen of the other. We already did the proof for this one, right? All it is the previous formula where you just plug E in for A. I did it. So if I look at this guy, this is a chain rule, right? So the outer function is the natural log. The inner function is x cubed plus 1. So the derivative of the outside is 1 over the insides times the derivative of x cubed plus 1. So that's going to be 3x squared over x cubed plus 1. Everybody's okay there? Or in general, if I take the derivative of the natural log of any function, it's going to be 1 over that function times the derivative of the inner function. Same idea. This is just the chain rule specific to the natural log as the outer function. Are these formulas worth memorizing here? No. Like it's just a special case of the chain rule where the outer function is the natural log, right? No big deal. All right, let's do another. Let's say we're do the derivative of the natural log of sine of x. What do you notice here? It's a chain rule, right? What's the outer function? Natural log. So the derivative of natural log is 1 over the inner function. And then times the derivative of the inner function. The derivative of sine is? So I'm left with cosine over sine. Who recognizes that? That is cotangent. What do you guys think? Pretty sweet so far. NBD. All right, let's do the next one. What do you notice when you look at example 3 here? Yeah, to do the derivative, what are we going to have to do? Okay. So what do we need to do the derivative now? What rule are we using? Well, it's a chain rule first, right? The outer function is x to the 1/2, and the inner function is natural log of x. So to do x to the 1/2, now we're using the power. So that's going to be 1/2 inner function to the negative 1/2 times the derivative of the inner. And that's probably how it would be written on a multiple choice. Does everybody see that on how I got to that final answer? Derivative of the natural log is 1 over x. I put the 1 over x and 1/2 together as 1 over 2x. And then I rewrote the negative exponent as a reciprocal and a radical. So the negative exponent makes it 1 over, and the 1/2 makes the square root. You guys see that? It's okay? All right, let's look at the next one then. What do you see? Chain rule is correct. What's the outer function? Log base 10, right? So I have the derivative of the outside, which will be 1 over 2 sine x times the natural log of 10 times the derivative of the inner Does that all look okay? What's the derivative of 2? 0. What's the derivative of sine x? Cosine x. So we have that as our final. Everybody okay there?
Is that natural log 10?
Mm-hmm.
Is that log 10?
So the natural log 10 comes because I'm using this property, because instead of having natural log at the start, I had log base 10. So I have to use that rule instead of just 1 over x. Does that feel okay? Everybody's okay? All right. So let's say we want to do the derivative of the natural log of x plus 1 over square root of x minus 2. When you see this, what do you see? Well, first is a chain rule. Inside of the chain rule, we have a quotient rule. Inside of the quotient rule, we're going to have another chain rule. Yuck, Mr. Kulik. Yuck. All right. So let's start this off. So the derivative of the outside is 1 over the inner times the derivative of the inner So far, so good. Now, when I outright 1 over a fraction, what am I really doing here? Reciprocal is the correct thing. If you know the answers, you don't have to just whisper it to yourself. Like, yell them out. Be loud and proud, man. So that first fraction, I can just turn into that. Then I have the quotient rule. So it's the bottom times the derivative of the top minus the top times derivative of the bottom. But to do the derivative of the bottom, what do I need to do? That'll be a chain rule over the bottom squared. I notice boom, boom, those guys cancel. So to do this, there's that. And what's the derivative of x minus 1, or x minus 2, excuse me? Just 1, right? Okay. So what do we got now? So we have square root x minus 2 times square root x minus 2 minus x plus 1 times 1/2 square root x minus 2 to the negative 1/2. Let's do one of those guys there. Over x plus 1 times x minus 2. Yucky, yucky, yucky. All right, let's distribute this through. Yes.
For tests, we have to distribute it through.
Well, if it's a multiple choice question
Yeah, but like for tests.
on a free response, you would not. So x minus or square root x minus 2 times square root x minus 2 is just x minus 2, right? And what's square root x minus 2 times x minus 2 to the negative 1/2? When I multiply those together, what do I get? 1! Right? Because the base is the same. We add the exponents. You get an exponent of 0. Ooh la la, I like that. So far, so good. Let's get that 1/2 out of there. Ugh. Right? That was pretty rough. What if I told you there's kind of an easier backdoor to this problem? You're like, I'm listening. You had my attention before, but now you have my interest. What is that? What is the interesting or what is the helpful backdoor to this problem? I'm doing algebraic rearrangement of what I have here. How many of you guys remember in Algebra 2 when we asked you to expand or compress the logarithm? Does that sound like a familiar problem type? That's what we're going to do here, is I'm going to expand this logarithm. So when I have the log of a quotient, how can I rewrite that? Okay, well, I should rewrite these then, huh? So it's log of the numerator minus log of the denominator. You guys remember that? What if I have log of a product? Well, it's log of the first factor plus log of the second factor. And then what if I have log of an exponent? Well, that's the exponent times log of the base. Everybody's okay there? Remember those three properties of logarithms? So if I look at that previous problem, I can rewrite that as the natural log of the top minus the natural log of the bottom. Everybody's okay there? And then I recognize that, hey, that square root is the same thing as an exponent of 1/2, right? So I can do that. So far, so good? Okay. Now I'm going to go ahead and do the derivative of each of these separately. What's the natural log of x plus 1? 1 over x plus 1 times the derivative of x plus 1. Great. What's the derivative of the natural log of 1 or x minus 2? 1 over x minus 2 times the derivative of x minus 2. What's the derivative of x plus 1? What's the derivative of x minus 2? So here we just have 1 over x plus 1 minus 1/2 times 1 over x minus 2. And if I make a common denominator there, I'd have 2 times x minus 2 minus x plus 1 over 2 times x plus 1 times x minus 2. Is everybody okay with how I got the common denominator there? I skipped some steps. That's okay though. And I guess where I end up at. Same spot as before, right? Which procedure did you prefer? That second one seems massively nicer. A little bit more algebra at the beginning, but how much easier was the calculus? Not having like chain rule, and then inside of that a quotient rule, and inside of that a chain rule. Yuckarooski. If I have a logarithm there, I can use it to kind of like unlink a lot of those properties, which is nice. I hate having the ones nested inside of the other, nested inside. That gets pretty complicated to use. A logarithm allows me to kind of unnest that stuff. What do you guys think? Okay? All right. All right. So here we have the derivative of the natural log of the absolute value is still just 1 over x. You remember here earlier, we were looking at these problems, and where was that guy? Ah, right here. Remember how we had the absolute value in there and we just kind of ignored it? This is why. Now, it seems a little strange that we're just going to ignore that all willy-nilly. Should we kind of prove that? So just using our normal definition of the absolute value, I can say this, right? Why are both of them strict inequalities? Why are neither of them or equal to? That's not a typo, that's on purpose. Because I can't do the natural log of 0, right? Even if I have the absolute value around it, there's still natural log of 0. Can't do that. Everybody's okay? So if I do the derivative then, what do I get for the derivative of the natural log of x? 1 over x, right? What do I get when I do the derivative of the natural log of negative x? 1 over negative x times the derivative of negative x. What's the derivative of negative x? And what do I get then? Just 1 over x. Oh, Mr. Kulik. Very sneaky. Everybody's okay there? So again, that's like the second or third time we've used that definition, that piecewise definition for an absolute value to deal with a problem. We're adding an absolute value in it. All right. Let's take a look at this terrible, terrible, terrible looking problem. When you look at this problem, what do you see? I see a quotient rule first. Inside of that quotient rule, I then see how many chain rules, though? I see 2 and a product rule. Oh my God, this is like a nightmare, Mr. Kulik. Are you telling me I have to be able to do stuff like this? Absolutely. All right, so what is this? What would this look like? So it'd be the bottom times the derivative of the top. Who's sick of that projector? I am like ready to just punt it like a football. You guys would back me up that it just like fell off the wall, right? It's like, I don't know, Mr. Kanja. The thing just fell off the wall. That's not my footprint on it. What do you mean? It must have just fallen off the wall and landed on my foot. So I'd have that, right? That's my quotient rule. That's to start. To do this, what am I going to need to do? Well, product rule is going to come first, right? And then to do this one, what am I going to need to do? Yeah, that's a chain rule. Ugh. All right, let's keep going. To do this derivative, what do I need to do? Chain rule. Oh my God, Mr. Kulik, this is like a problem that just never ends. I prefer to think about it as the problem that just keeps on giving. I got some scoffs on that one at least. They're like, yeah, that's what I'll call it. The problem that just keeps on giving. I'm going to do the chain rule here all in one step. Is that okay with you guys? That's where the 2x came from. I'm just getting sick of great googly moogly now. Let's see here. Let's try to see if we can do any reducing here first. I notice that I have some 3x's plus 2. Everybody see that? What's the least common multiple for those 3x's plus 2's? It's to the 4th, right? So all of those can go. That can knock down to 1. That can knock down to 6. Everybody feel okay there? Next thing I want to do is let's get rid of all these stupid fractions floating through here. I hate that. So I'm just going to multiply the top and bottom by 4. So that just lands in there once, but then it'll land in there and in there. So when it lands in here, that's going to give me a 2, and then another 2, that's going to be 4, and then x to the 3/4 times x to the first is going to be x to the 7/4. That's 2060. Who's sad yet? It's pretty bad, right? Keep going, like that's no way that's going to be the simplified answer in the multiple choice question. Let's see. When I look in here, I'm going to factor out maybe not. Let's see. I'm going to factor out one of these guys. I think I'm going to factor out one of this. And now it's going to turn into an x squared plus 1. Oops, negative 1. That's not quite right. Oops. Yeah, this is just getting yucky, right? Who's like, I sure hope Mr. Kulik is showing me this for a reason, right? This is grossapalooza. Yeah, you're like, there's got to be a simpler way, right? You got it. Are you guys ready to give up on this? Great. Guess what I'm going to do to start here? Oops, that's not what I thought that was going to do. That's a weird thing that you just did here. All right. What if I start, get ready, this is going to make life much easier because I am going to give you something like this on a test. Yeah, because if you don't know how to do the back door, this becomes an enormous like pit of time. With the back door, it's not so bad. Here's what I'm going to do. I'm going to start by just taking the natural log of both sides of this equation. You can do that, Mr. Kulik? Absolutely. What good does that do? Well, now I can expand this logarithm, right? Now let's write it that way. And I can do that. So far, so good. Now I'm going to differentiate. What's the derivative of the natural log of y? Close. There you go. What's the derivative of natural log x? Okay. What's the derivative of the natural log of x squared plus 1? 1 over x squared plus 1 times 2x, I heard somebody say. What's the natural log of 3x plus 2? Good. Calculus is done now at this point. Just some cleanup left. Way easier so far, right? All right, let's make a common denominator here. What's our common denominator going to be? It's going to be x times x squared plus 1 times 3x plus 2. Everybody see that? It's going to be 4, right? I am going to just like snap one of these days. When Mr. Kulik snaps, you guys can all say it was because of that darn projector. Everybody's okay with this? Just made a common denominator. Now it's messy still. Now we'd have to FOIL this stuff out here, but rather than yeah, I guess we do. So what do we get? We get 3x cubed times 3, that's 9x cubed. And then 2x squared times 3, so that's 6x squared. And then 3x times 3 is 9x. And then 2 times 3 is 6. Shh. That's 4x squared times 3, that's 12x cubed. And then 4x squared times 2 is 8x squared. And then 4 times 15 is 60x times x squared is minus 60x cubed. And then we have minus 60x. Oh my God, I'm going to kill this thing. So we have 9 and 12, that's 21, minus 20, or minus 60 is, what, 29? No, 39. We have 6 and 8, that's 14. We have 9 and negative 60 is negative 51. All right. Here's the unfortunate part. It's not done. What's wrong? Got to get dy dx by itself, right? But I'm not going to write it as y. I need to write it as what y equals. I'll just make that a sixth. And that, I think, is as good as we can do.
Where do you get that second portion? X7.
That's 3/4.
Oh.
And really, this was like that is all y. Then I'm just tacking on back to the end there. But I would argue still that was way, way nicer than going and trying to do it without the logarithms. Way, way nicer. Not nearly as much crap to keep a hang on. Like the simplifying was much nicer. This looked nasty without it, right? Was pretty darn nasty without it. All right. One last, and then we're done. What if I ask you to do the derivative of y equals x to the square root x? Mr. Kulik, what the heck am I supposed to do with that? Well, let's do logarithmic differentiation. So that will reduce down to just x to the negative 1/2. And I could maybe like make a common denominator or whatever, but good enough for me. What do you guys think?
Why is it 1/x?
The natural log of
Yeah.
the derivative of the natural log? Okay. All right. So for next time, there you go. That's 3/6. Just looking ahead, the plan here will wrap up 3/7 next time. Friday will be like a general review day, and we're probably looking at test beginning of next week, Tuesday of next week.
You might What area are you going on the list for here? A or B?